So we're going to get into the idea of some simpler ways to be able to take derivatives rather than always having to use your IROC formula. The limit is h approaches 0 of f of x plus h minus f of x all over h. So we're going to look at some patterns you may have noticed, you may not have. But if you just think of a constant function, which is a horizontal line, our slope we should know is 0. So therefore, if I was doing the derivative of a constant function, then we would know our slope would be 0, because once again, slope of our tangent line is the same thing as our derivative. Well, here we have a linear function, f of x equals mx plus b. Well, we know our slope then is always our m, so that means our derivative would be m. Now, in the past, we've already done the derivative of this here, which of x squared, and ended up with a 2x. Or when we've done a problem like this before, f of x equals x plus 1 over x, we ended up with this here. I don't know if you've noticed a pattern, but if we had a problem like this, you really get for your derivative a 3 with an x squared. For the most part, it ends up that what was your exponent goes down in front, and your exponent on your derivative is 1 less. So that's what we're saying here in general. If you have x to a power, to find its derivative, you put the exponent down in front. That's what we're doing with our n. And we're decreasing our exponent by 1, so it's n minus 1. This is referred to as the power rule, because you have x to a power, and so then to find your derivative, you just put the exponent in front and decrease it by 1. So here, we could take our derivative. Well, 2 is a constant, and we just said, once again, to clarify up here, the derivative of a constant is 0, so that goes to 0. Then we would have this. You put the exponent down in front with this, get a negative 6, because 2 times that negative 3 is negative 6. Decrease your exponent on the x by 1, so we get this for our derivative. Same idea works here when we're doing our derivative of this. Oh, I see there's an issue. I have f of x when it should be an f of t in each one of these, and f prime of t. You put your exponent in front, decrease it by 1, we get this here. Then we do the derivative of 5, which is a constant, which is 0, so we're not going to write it. So as long as it's written as something to a power, we can do the power rule. Now, it doesn't work when your variable's in the bottom. However, we could bring this up as a negative exponent. Remember, it's a 1/2 because it's a square root. Bringing it up from the bottom means it's negative. So this is just rewriting your original problem. Now that it is written as something to a power, we can do the power rule. So to take our derivative, we'd have to take our exponent of negative 1/2, put it in front. Then we'd have to decrease our exponent of negative 1/2 by 1. In other words, we're taking negative 1/2 minus 1, and so then we get negative 3/2. At this point, since we started out with roots, I'd probably end up my final answer with roots, so I deal with my negative exponent, taking this down to the bottom. This right here would cause a negative 1 to be on top with a 2 being on the bottom, and so we would get a negative 1 on top, or 2 being on the bottom. This goes down, and you could write that as a root if you wanted. Even if you have a fractional exponent, it works. But it does have to be x to the power. So if it's in the bottom, you got to bring it up as a negative exponent and then do your derivative. So here we'd have x to the 1/3. So to do our derivative, we'd put our exponent of 1/3 in front, decrease your exponent by 1. 1/3 as your exponent, minus 1 is a negative 2/3. That negative exponent puts it in the bottom. The 1/3 causes a 3 to be in the bottom. And then you could write this right here as a root, so that would be the cube root, because that's the denominator of the exponent of an x squared. So here's a quick overview of the proof of our power rule. We have our basic IROC here. If we have x to the n power, you would then have an x plus h to the n power minus f of x, which is your original x to the n power. Now, you could go ahead and FOIL this out. Technically, you're doing the binomial theorem, which we would have here. Don't be real concerned about that. But just know that you would, when you work this out, you'd have an x to the n power plus an x to the n minus 1 times an h with a number in front, plus you keep going down by 1 each time on your power of x, so you'd have that with lots and lots of terms with h's hanging out by them. And then eventually you get to where you just have an h to the n power at the very end. Still minus your x to the n. Now notice here we have our x to the n here would be canceled out with this here. And then all these have an h in them. This has got a h squared, this has got a h to the n minus 1, this has got a h to the n over an h. So you could take an h out of everything. So if you do that, taking an h out of everything right in this area right here, well, then you get what we have down here. So then you do your limit as h goes to 0. Well, there's no h's left, so it doesn't do anything to that. There's an h being 0 here, so it cancels out this term. There's an h being 0 here, cancels out that. H being 0 cancels out that. So you're only left with this here. So that's really the proof of your power rule in a quick overview. So go ahead, try to do your derivatives of all these. Put the exponent in front for your derivative. Notice it's f prime of t. Put the exponent in front, decrease exponent by 1. G prime of w, put the exponent in front, decrease your exponent by 1. This one here, your variable's in the bottom, so before you can do power rule, you have to write it as a negative exponent because your power rule only works as it's x to a power. Then you put your exponent in front, decrease your exponent by 1, and then you could write it back as a fraction again, dealing with that negative exponent, moving it down to the bottom. If there's a number in front, well, it stays there because it's going to be a 7 times that. Put the exponent in front, so you'd have a 4 times 7 in front. Still decrease your exponent by 1, so you get 28 to z cubed. Even if you have several terms added or subtracted together, you still do the power rule on each one. Exponent in front, 9 goes down with the negative 5, gives us negative 45. Decrease your exponent by 1. Take the 5 down with the 7, 7 times 5, decrease your exponent by 1. Put the 2 down in front, 2 times negative 25 is negative 50, decrease your exponent by 1. Exponent is 1, put it down in front, doesn't change it, decrease it by 1 would be an x to the 0, which is 1. And you might be wondering, why didn't we do anything here? Hey, do we have any variables here? No, we have a number. Pi is a number, pi squared is a number, times it by negative 12 is a number, so this is a constant. Remember, the derivative of any constant goes to 0. Over here, put the exponent down in front, decrease it, exponent by 1. Exponent in front, decrease it by 1. And this is a constant, so the derivative of that goes to 0. Remember, this is a constant because x to the 0 is 1. 1 times 5 is 5, so you'd be subtracting 5 to constant. When you do your derivative of the constant, it goes to 0. So find the slope of your graph at x being 2 for f of x equaling x plus 5. Well, to find your slope, you know you got to do your derivative. So you put the exponent in front, decrease it by 1. Looking for your slope at 2, you just have to plug 2 in for x into your derivative. And so then we get 2 to the 4th, which is 16 times 5, so we get 80. This is an 80, not an A and a D, but it is AD for your answer. Yes, that's an attempt at a bad joke. So here you're asked to find the equation of your tangent line to this graph of f of x equals x squared at x being 2. Well, to find the equation of any line, you need to have a slope and you need to have a point. So to find your slope, you know that that's going to be dealing with your derivative. to do our derivative of this, it's extra power. We could just do our power rule, and we get our derivative to be this. We're looking for our slope when x is 2. Remember, your derivative is your slope predictor function. So we could plug it in and go 2 times 2, plug in 2 being x, get 2 times 2, we get our slope to be 4. So our slope is 4, and we have our point. So if you have a point and a slope, you could use your point slope formula. You might be wondering, how did you get the y value to be 4? Well, if you're looking for your y value, can't you just take 2 and plug it into your original function? And that will give you the y value of that point. So that's how we get that. Now that we have our slope being 4 and we have our point 2, 4, use our point slope formula, y minus the y value of our point, equaling our slope, which we said was 4, x minus the x value of our point, distribute through, get y by itself. So remember, this means derivative of sine, so the derivative of sine is cosine. Or the derivative of cosine ends up being negative sine. Make sure you know these. These are part of your vocab. But here's a quick overview of the proof. You could do your normal IROC of this. So it'd be sine of x plus h minus sine of x over h. Here you'd have the sine of two things added, so you have a formula on your calculator cheat sheet cover from pre-calc that allows you to go ahead and expand that out. And so that's what we did here, still with your minus sign. So here we're going to go ahead and rearrange this a little bit. Basically, we're going ahead and we're taking this with this, putting it together, and we're going ahead and taking this and putting it down here. So the two red things are going here. Now, that's going to help. When we look at the red, we could go ahead and factor out a sine, and we're left with a cosine minus 1 over h. Here, I'm going to write this as a sine h over h with a cosine by it. Remember that this right here, limit as h approaches 0, is your basic trig limit. When you do your derivative of this, that's also hanging out in your limit chapter from next to your basic trig limit, and that's 0. So you'd really get the sine of x times 0, and you get 1 times cosine. So in other words, you get 0 plus cosine, or just cosine. You could do a very similar type of proof on this one here to be able to prove that your derivative of cosine is negative sine. So let's do our derivative of this. We have extra power, so put your exponent in front and decrease it by 1. Then it would be a 2, and then you should know from the last slide that your derivative of cosine is negative sine. Well, a negative times a negative, we can just write that as a 2x plus 2 sine x for your derivative. Notice I wrote a y prime equals. Whenever you're dealing with your derivative, you need to indicate that you're dealing with your derivative by writing y prime or f prime of x or something along that lines. So your derivative is a rate of change. Your instantaneous rate of change. There's all kinds of rates of change in real life. Population growth rates, production rates, water flow rates. Your velocity is really a rate of change. It's your rate of change of your distance over your time. Acceleration is a rate of change of your velocity over time. So we know from the earlier CPM unit that the derivative of your position is your velocity, meaning derivative of position or distance is velocity. Your average velocity is just the change in your distance over the change in your time. Average velocity would also be like your average rate of change, the slope between 2 points. Change in time over change in change in distance over change in time. Now, if you're looking for acceleration and you're given velocity, you should know that from the CPM chapter, that if you do the derivative of your velocity, it gives you acceleration. So in other words, if you have your distance or position and you do your derivative twice, that's what the double prime means right here. You go from distance Do your derivative once, that's velocity. Do it a second time, that's acceleration. So looking at your position, um, which is your distance, or the height of an object being thrown into the air, it's given to you by this equation here. Your y naught is your initial height. Your v naught is your initial velocity. G is your acceleration due to gravity. Now, acceleration due to gravity, we would say is 9.8 if you're dealing with meters per second squared. If you're dealing with feet, it would be 32. So if we have this right here, and you were looking at, which is your distance, and you were looking for velocity, you just have to do your derivative. Well, the derivative of this initial height is a constant. That would disappear, and that would just go to 0. Your derivative of t to the first times a number would just be that initial velocity. Here you'd put your exponent down in front. It would cancel out that negative 1/2. G is just a number, so it's not a variable. T is your variable. So you would get your derivative of your distance is your velocity, and it's given to you by this. If you do your derivative again, then you would get your acceleration. Now, if you were throwing an object up in the air and it would come back down, at the very highest point here, you're not going up, you're not going down, your velocity would be 0. So you'd be going up and down. Right up here, your velocity would be 0. Now, when you're going up, we would say your velocity is positive. We would say it's positive because your distance from the Earth is increasing. When you're coming back down from the top point, we would say your velocity is negative because your distance to the Earth is decreasing. So here we have at time equals 0, we have a diver that jumps from a platform that's 32 feet in the air, hence initial distance is 32. And we're dealing with feet, so we know that negative 1/2 g t squared, g would be 32, negative 1/2 times 32 is negative 16. And we would know the initial velocity is given to you by this. So this is our distance. We want to know, when does the driver hit the, or diver hit the water? Well, that means the height of the diver would be 0 because the water is your, or we're measuring height above the water. You're not above the height of the water, so it's 0. So you'd plug in 0 right here. Now it's just a nice normal quadratic to solve. I might go ahead and divide both sides by negative 16. Just a nice normal quadratic. In this case, it factors quite nicely. We solve it, we get 2, and we get negative 1. So at this point, you got to think, oh, well, t is representing time. So we could have a velocity or a time of 2 seconds, but it doesn't make sense to have a time of negative 1 second. So we would know our time is 2 seconds. The second part of this question is, when or what is the velocity when the diver hits the water? Well, velocity, we just have to do our derivative of this, and so we could just do our normal power rule of this, putting exponents in front, decreasing it by 1. And we want to know what's our velocity when we impact the water. Well, we know it takes us 2 seconds to get to the water. All we then have to do is just plug in 2 into our velocity. Negative 32 times 2. And then add 16, we get negative 48. So in other words, with units, it would be negative 48 feet per second. Now we know in the context of this problem, it would be negative because your distance to the water was decreasing.